Hi, in this video, we are going to look at another proof method, which is known as the proof by construction. So we'll see different types of example problems in this video, and we'll look at how, depending on the problem, we can construct functions. We can sometimes even construct geometrical figures that help us prove a particular statement. So you should find these examples quite instructive, like go through the problems and try them yourself, and then you can look at the solution. So hopefully this will teach you a new method to do proofs for Olympiad problems. We start off with the first question. This is suppose that x1 is greater than x2 is greater than equal to x3 is greater than equal to x4 is greater than 2. These four numbers are all greater than 2 and they are ordered in this way. And x2 plus x3 plus x4 is greater than equal to x1. Okay, we have to prove that x1 plus x2 plus x3 plus x4 whole square is less than equal to 4x1, x2, x3, x4. Okay, so this is a problem. Obviously, you can try and approach it in many different ways, but we will look at it in a slightly unique way. So let's say we denote A by x2 plus x3 plus x4, and we call B as x2, x3, x4. Okay, so we are taking two new variables, A is this and B is this, and then the original inequality looks like x1 plus A whole square is less than equal to 4x1b, right? The LHS is basically becoming x1 plus A whole square, and this is 4 times x1 into b. So this is what we have to prove, which is equivalent to x1 square plus excuse me, plus 2 times A minus 2b into x1 plus A square is less than equal to 0. This is the original inequality converted in terms of our new variables A and B, right? So if you say let f of x equal to x square plus A minus 2b x plus A square, we need to prove that f of x1 is less than equal to 0. That is our target here. So let's work on this in the next screen. We have f of x is equal to x square plus 2 times A minus 2bx plus A square. And we need to show that f of x1 is less than equal to 0, right? Now the discriminant of this quadratic is basically 4 times A minus 2b whole square minus 4A square, which is equal to 16 times b minus A. This is my discriminant, and from the original definitions, A was x2 plus x3 plus x4 and B was x2, x3, x4. So what is A by B? A by B is equal to x2 plus x3 plus x4 by x2, x3, x4, which is equal to 1 by x3, x4 plus 1 by x2, x4 plus 1 by x2, x3. This is my A by B, right? Also in the problem they had said that x1 is greater than x2 is greater than x3 is greater than x4, and all of them are greater than equal to 2, right? So this implies that x3, x4, x2, x4 and x2, x3 are all greater than equal to 4, right? So obviously the reciprocals will be less than equal to 1 by 4. We can write less than 1 by 4 plus less than 1 by 4 plus less than 1 by 4. So from here we get a by b is less than equal to 3 by 4, which means that a by b is less than 1, which means that b is greater than a. So b minus a is positive. So in our discriminant, we have 16 times b minus a. So clearly b minus a is positive and b is positive. We already know that. Therefore, the discriminant is positive, right? So if the discriminant is positive, the quadratic parabola looks like this. It is an upward facing parabola and positive like this. So clearly it must have two roots. The roots could be called u and v, let's say. So the intersection points of this parabola with the x-axis, which is the roots, are given by 2b minus a minus 2 times root over b minus a, and v is 2b minus a plus 2 times root over b minus a, right? I have used the quadratic formula to find the two roots, right? We need to prove that x1 lies between u and v. Why do we need to prove that? Only if x1 lies between u and v, then only the value of f of x1 will be less than equal to 0, right? So our job is technically now to prove x1 lies between u and v are given by the roots of this equation, right? Great. Now let's work on the next screen. We have a was equal to x2 plus x3 plus x4. That was our assumption. So obviously, since this is given to us, x1 is greater than x2 is greater than x3 is greater than x4 is greater than equal to 2. This was given to us. Therefore, x2 plus x3 plus x4 is less than, obviously, x1 plus x1 plus x1. So, which is equal to 3x1. So, therefore, that proves that x1 is greater than equal to a by 3. Right? Correct. Also, x1 is clearly less than x1 is greater than a by 3, we have already gotten, and it has also been said that x2 plus x3 plus x4 is greater than equal to x1. That was also a condition of the problem. So we know that a is greater than x1. So we already know x1 belongs to a by 3 to a. From this and this, we know x1 belongs to a by 3 to a. So now it is sufficient for us to show, our job was to prove that x1 lies between u and v, but we already know that x1 lies between a by 3 to a, right? So if we can show that a by 3 to a, this interval lies between u and v, then our job is done, right? So in order to prove that, we need to show that u is less than equal to a by 3 and a is less than equal to v. If we can show this, then a by 3 to a is an interval that is contained completely inside my u to v, which will mean that x1 lies completely inside u to v, right? Great. So let's try to prove this part first. Our definition of v was 2b minus a plus 2 times root over b minus a, which is clearly greater than 2b minus a because the second part is positive, and 2b minus a is greater than a. Why? How do I know that? Because we have already shown that b is greater than a. So if b is greater than a, this is equal to b plus b minus a. So this is positive. So that is obviously greater than a, right? So first part is already done. This we have already shown now. So now we have to just show that u is less than equal to a by 3, right? So let's work on that in the next screen. U was equal to 2b minus a minus 2 times root over b into b minus a. So this we can simplify and write like this: b plus b minus a minus 2 times root over b into b minus a. So it is clear from here that u is equal to root b minus root of b minus a whole square, right? Okay, that should be obvious. This I'm just using a square plus b square minus 2ab formula. And now here I can transform this and write it as a by root a plus root b minus a, root b plus root b minus a whole square, right? Root b minus a. And if I multiply it with root b plus root b minus a, what will I get? B minus b minus a, correct. So I'll get a. So this is correct. I'm just saying that this radical expression, I'm writing it in terms of its conjugates like this, right? Great. So this is equal to a square by root b plus root b minus a whole square, which we can rewrite by saying a by, and the extra a I will take in the denominator, the extra a. So I will say it is root p plus root p minus a whole square by a. So that becomes basically, that can be written as a by inside this is root a whole square. So I can bring a root a inside. I can write it as root p by a plus root p minus a by a whole square. Think about it. All of these transformations are the same thing. I have taken the a into the square root and written it as a root a. So I have divided by root a. So this becomes a by root b by a plus root over b by a minus 1 whole square, right? Now, we know, we have earlier proved that a by b is less than equal to 3 by 4. If you remember, we had done a by b is less than equal to 1 by 4 plus 1 by 4 plus 1 by 4 at an earlier stage. So if a by b is less than equal to 3 by 4, then b by a is greater than equal to 4 by 3, right? And we'll employ that here. So we'll say if you replace b by a with a greater number here, right, then the whole thing will be smaller, right? Correct. So this is less than equal to b by a is greater. So actually I am replacing it with a smaller number. So therefore the whole thing is lesser than a by root over 4 by 3 plus root over 4 by 3 minus 1 whole square, right? Which is equal to a by root over 4 by 3, which is 2 by root 3 plus 1 by root 3 whole square. So actually this is going to be 3 by root 3 or root 3 whole square. So this is a by 3, right? So technically what I have shown here is u is less than equal to a by 3, right? Go through the steps of the process again. What we have basically proved is that we showed that v is greater than a and we showed u is less than a by 3. So that means that u to v, the interval u to v, it already contains an interval of a by 3 to a, right? And we have already decided that x1 lies between a by 3 to a. So therefore x1 lies between u to v. And if x1 lies between u to v, f of x1 was less than equal to 0. And that is what we needed to prove in order to finish the question, right? So that's an interesting question where we chose a quadratic function. We chose first of all nice variables like a and b, which made the whole question having, instead of having 4 variables, we were down to a single variable x1, right? And these two parameters a and b. And it became a quadratic function and we used properties of quadratic graphs in order to solve the problem. Let's go on to the next question. This question is a very famous question. It's the question from the 27th International Maths Olympiad. And it's one of the questions that got the least score on the Olympiad. So one of the toughest questions of that Olympiad. So it goes like this. Suppose that every vertex of a regular hexagon, like regular pentagon, corresponds corresponds to an integer such that sum of the 5 integers is positive. Sum of the 5 integers is positive. If the integers corresponding, if integers corresponding to 3 adjacent vertices are x, y, and z with the middle y less than 0, then do the following adjustment. What is the adjustment we have to do? We have to replace xyz with x plus y minus y and y plus z. We have to do this adjustment. If there are still negative numbers among the remaining 5 integers, repeat the process. And the question is asking, can such transformations be terminated necessarily? Can this process or this transformation be terminated necessarily after finite number of steps? Necessarily after a finite number of steps. So what is the question saying? So there is a regular pentagon. For each vertex of the pentagon, you are assigning a random integer. Some integers have been assigned, and if the integer corresponding to the middle vertex, if you take any 3 vertices of the pentagon x, y, and z, and if the middle vertex of that pentagon has an integer y which is less than 0, you can do a transformation where you can change x, y, and z to x plus y minus y and y plus z, right? So that is my basic transformation. It converts that middle vertex to positive, right? You can see that y will become minus y. It makes that middle vertex have a positive integer. It doesn't say anything about the other 2 vertices. Other 2 vertices could have been converted to negative values because of having to add x plus y and y plus z, right? However, the process says that if you still have negative integers, you have to repeat the process again and again, right? The question is, can this process be terminated after a finite number of steps? So can we basically ensure that after a finite number of steps, there are no further negative integers in the whole pentagon, all 5 vertices of the pentagon? So that is the question. Now, in order to solve this question, you have to realize some way to mathematically or quantify what happens in that transformation, right? What happens is clear visually, x, y, and z becomes this, but there must have been some change to that, to the figure and to a function possibly. You could possibly construct a function that denotes the transformation. And once you construct a function, you have to understand what change happens in each step of the transformation and whether eventually all the negative numbers will disappear or not, right? So there are many ways to solve this problem, but all of them rely on constructing a function that captures the transformation. And there are several possible suitable functions. You can try and think of one yourself and see whether you are able to conclude something from here. But this is the standard method. So we have this situation. This is my pentagon. Let's say we have labeled its vertices with integers v, w, x, y, z. The question has said that v plus w plus x plus y plus z is greater than 0. The sum of all the integers was positive, and we can assume right now that here y was negative. We can assume y was negative. So v, w, x, y, z after the transformation will become, after one step of the transformation, will become v, w, and x, y, z will be converted to x plus y minus y and y plus z, right? This is one step of the transformation. So now we have to think of a good function that will help us capture the essence of this. So we construct this function. Construct the function. It's a function of 5 variables. Function f of x1, x2, x3, x4, x5 is equal to x1 square plus x2 square plus x3 square plus x4 square plus x5 square plus x1 plus x2 square plus x2 plus x3 square plus x3 plus x4 square plus x4 plus x5 square, and finally x5 plus x1 square. This is the function that we will construct. So this function takes inputs as the integers corresponding to the vertices of the pentagon, and it calculates out this value x1 square, x2 square, x3 square till all the integers squared, and then sum of them two at a time in a cyclic manner. x1 plus x2 whole square, x2 plus x3 square, x3 plus x4 square, x4 plus x5 square, and finally x5 and x1 square, right? Okay. So what we want to understand is what happens before and after a transformation. So we want to find out the value of f of v, w, x plus y minus y, y plus z. This is the value of the function after the transformation minus f of v, w, x, y, z. We need to calculate this. So let's evaluate the function here. It will be v square plus w square plus x plus y square plus y square plus y plus z square. I am writing the value of the first function. Now I have to take the sum of the terms two at a time, right? So v plus w square plus w plus x plus y square plus x square plus z square plus v plus y plus z whole square. This is the first term, and then we subtract from here this stuff, minus v square minus w square minus x square minus y square minus z square minus v plus w square minus w plus x square minus x plus y square minus of y plus z square, and finally minus of v plus z square. So now notice that many things can get cancelled here. This gets cancelled, this gets cancelled, x square gets cancelled, y square gets cancelled, and z square gets cancelled. We have x plus y square getting cancelled here. We have y plus z square also getting cancelled here. And now we are left with, okay, v plus w square also gets cancelled. Now we are left with this minus this and this minus this, right? So think about it. This can be expanded and written as w plus x whole square plus y square plus 2y w plus x. And this can be written as v plus z whole square plus y square plus 2y v plus z. And we have subtraction w plus x whole square minus v plus z whole square. So these two get cancelled here. And eventually we have 2y square plus 2y v plus z plus 2y w plus x. And so we can take 2y common, and we have y plus v plus z plus w plus x, right? Now think about it. we have been already told that this quantity, the sum of all 5 integers, is positive. So this is positive, and we know that this is negative, right? So what we are getting is the overall difference of functions is a negative quantity. This is negative overall. So what that means is the final value of the function is lower than the initial value. Okay. So, and also if you look at the nature of the function itself, if you look at the nature of the function v, w, x, y, z, the function was built up of all of the squares and all, right? All of the squares like this and all of the squares like this. So it should always gives a positive output. Always gives a positive output. And what happens after one transformation? The value reduces. We have proved that after one transformation, the final value of this function value reduces after one step of the transformation, right? So if the value is reducing after one step of the transformation, and we know that these are integers, b, w, x, y, z, all of these are integers. So the value of each value belongs to integer positive, and it is reducing in each step. Every time you do a transformation, it reduces. So that means it will reduce by steps of at least one integer or more than that, right? And that means since it always has to be positive, there are only finite number of times you can do this transformation. Only finite number of times the transformation can be performed, because if you start off with some integer value here n, you are going to reduce it in every step. At least it becomes n minus 1 or n minus 2 or something lower than that, right? And every step it reduces in each transformation. So obviously by that infinite descent method, you cannot keep reducing and keep ending up with positive integers forever. That will end after a finite number of steps, right? So eventually that proves that the sequence of transformations must terminate after a finite number of steps. So that is the solution of this one. Let's move on to the third one. Here, suppose we have positive real numbers x, y, z, which satisfy x square plus y square by 3 equal to 4, y square by 3 plus yz plus z square equal to 4, and x square plus z square plus xz equal to 4. We have to find the value of 2xy plus yz plus 3xz. Okay. So in this question, we look at these three equations, right? These are positive real numbers that are doing this, that are satisfying this. So think of these equations. You should see a pattern here. X square plus y by root 3 whole square is 4. And then we have y by root 3 whole square plus z square plus yz equal to 4. And x square plus z square plus xz equal to 4. So like here you can see that y by root 3 is present in both the equation and x and z are there. So what we will do, it's a tricky idea, but the idea is pretty simple. Once you realize the idea, it seems pretty obvious. So we will draw an xy plane, and this is the origin. Let's draw OA like this, OB like this, and OC like this. And let's call this distance as x, this angle as 90 degree, this angle as 150 degree. So obviously this angle will become 120 degree. And this OB distance is given by y by root 3. And this OC distance is given by z. And OA distance is x, right? Now think about it. If I join AB, BC, and CA, what is the length of the side AB? Length of the side AB will be given by cosine rule. Cosine rule in this triangle, right? And it's a right angle triangle, so actually just perpendicular Pythagoras theorem. So it will be root over x square plus y square by 3, right? And notice that in the question they have said that that is 4, so that is equal to 2. Again, this distance, the angle here is 150 degree. This is y by root 3 and this is z. So now you can say cosine rule, the distance here is y square by 3 plus z square plus 2 y by root 3, no, minus 2 y by root 3 z cos 150 degree, which is equal to minus of cos 30, so minus root 3 by 2, and root of that should be BC. And you will realize that minus root 3 by 2 will cancel this and it will become root over y square by 3 plus z square plus yz, which is what is given here is 4. So this is also 2. Basically, apply cosine rule, you will realize that BC length is 2 because of this relation. Similarly, apply cosine rule here, it will be x square plus z square minus 2xz cos 120 is minus half and root of that. So again, it becomes x square plus z square plus xz. So basically that distance is also 2. So what we are ending up having is the question is becoming like this. There is OA, there is OB, and there is OC. And these are such that these distances are all equal. This is an equilateral triangle. OA was x, this was y by root 3, this was z. This angle was 150 degree, this angle was 120 degree, and this angle was 90 degree, right? So now what we can say is area of AOB plus area of BOC plus area of COA will be equal to area of ABC. That is an obvious statement by the geometrical figure, right? Now, what is the area of AOB? Area AOB, it's a right angle triangle. So that is simply half into y by root 3 into x. Area of BOC will be half into y by root 3 into z into sine 150, which is 1 by 2. And area of COA will be half into x into z and sine 120, which is root 3 by 2. That should be equal to area of triangle ABC, and we have figured out that all the sides are equal. So it's an equilateral triangle of side length 2. So it is root 3 by 4 into 2 square, so 4. So what we are getting is this relation xy by 2 root 3 plus yz by 4 root 3 plus xz root 3 by 4 is equal to root 3, right? If you multiply throughout all the sides by 4 root 3, you will get 2xy plus yz plus 3yxz. You multiply this by 4 root 3, you'll get 3xz is equal to 4 root 3 into root 3, which is equal to 12. And this is what the question is asking you. Obviously, it is a tricky idea to think of, but once you think of it, it seems pretty obvious, right? There are possibly other ways to do it. Here, I wanted to show you one problem where we have constructed a geometrical figure to solve a, on the face of it, it looks like an algebra problem, right? Obviously, there will be other ways to do it. We have gotten the answer here by drawing a triangle, equilateral triangle, and noticing things, right? Let's go on to the next one. Question number 4. We have let n belongs to natural numbers, x belongs to R. You have to prove this equality. Prove that GIF of x plus GIF of x plus 1 by n plus GIF of x plus 2 by n, and so on till GIF of x plus n minus 1 by n is equal to GIF of nx. So obviously this problem can be approached in different ways, but what we will do is a nice proof on the basis of defining or constructing an auxiliary function. So what I will do is construct an auxiliary function f of x. My function is defined like this. F of x is equal to x plus 1 by n plus x plus 2 by n and so on, x plus n minus 1 by n minus of nx. My function is this. I want to eventually prove that this function is always 0 for any real numbers. If I prove that it is 0 for any real numbers, then my identity is correct, right? So how do I go about doing that? What I will show here is that this function f of x is periodic with period 1 by n. How do I prove that? I will just evaluate f of x plus 1 by n. So let's write the terms. It will become x plus 1 by n plus x plus 2 by n and so on plus x plus n minus 1 by n plus x plus 1, because when you add 1 by n to this, it will become n by n minus nx plus 1. This is what I'm getting, right? Now notice that this term can be split as GIF of x plus 1, and this term can be written as minus nx minus 1. So the plus 1 and the minus 1 get cancelled, right? And notice that the x has appeared again, which was missing from the first term. So this x can be written in the beginning of the column of the row of terms, and you are getting f of x plus 1 by n is GIF of x plus this till here minus nx, right? So actually, you can check it yourself. It is immediately obvious that f of x plus 1 by n is equal to f of x, right? So we have shown that f of x is periodic with period 1 by n. So f of x is periodic with period 1 by n. Now, if I want to show that f of x is 0 for all real x, and we know that it is a periodic function, then all we need to do is to show that it is 0 for x belongs to 0 to 1 by n, right? If it is 0 for this region, since it is periodic, it will keep repeating and it will always be 0, right? So now this is very trivial because GIF of x plus GIF of x plus 1 by n and so on till x plus n minus 1 by n minus nx. If x is belonging to 0 to 1 by n, where it is less than 1 by n, all of these terms are less than 1. So this is 0, this is 0, this is 0. This is also less than 1 because it is n minus 1 by n plus something less than 1 by n. And n times 1 by n, something less than 1 by n is still less than 1. So all the terms are identically 0. So it is obvious that function that we had chosen is 0 for x belongs to this. And we have already shown that it is periodic with period 1 by n. So our function is always 0 for all real x. And therefore, we have proved the statement of the problem, right? The problem is done basically. We don't need to show anything else. So that should be interesting. I hope you learned something from that one. Let's move on to the next problem. This says, let x1, x2, x3, y1, y2, y3 belong to real and satisfy x1 square plus x2 square plus x3 square is less than equal to 1. We have to prove that x1 y1 plus x2 y2 plus x3 y3 minus 1 whole square is greater than equal to x1 square plus x2 square plus x3 square minus 1 multiplied by y1 square plus y2 square plus y3 square minus 1. Okay, we have to prove this inequality. Now we are given these 6 numbers which always satisfy this condition. So we'll take two cases. Case 1 is when x1 square plus x2 square plus x3 square is equal to 1. In that case, you can see that the RHS is equal to 0 and the LHS is a perfect square. LHS is a perfect square, so it is always greater than equal to 0. So it is immediately done that LHS is greater than equal to RHS. The inequality is proved. So we'll look at the other case now where x1 square plus x2 square plus x3 square is less than 1 strictly, right? So for this particular case, what we'll do is we'll construct a quadratic function. Quadratic function. What is our function? F of x, f of t is equal to x1 square plus x2 square plus x3 square minus 1 times t square minus 2 times x1 y1 plus x2 y2 plus x3 y3 minus 1 times t plus y1 square plus y2 square plus y3 square minus 1. So notice that this function actually can be simplified a little bit. First of all, notice that the reason we have made terms like this is because we need terms like that. I need some way to write this as this discriminant, right? I want to say something about the discriminant of this quadratic, and from there I can conclude my inequality. So I've made a quadratic appropriately using the appropriate terms as the coefficients here. Now notice one thing, this f of t can also be written as x1t minus y1 square plus x2t minus y2 square plus x3t minus y3 square minus t minus 1 whole square. Why? Because you could always split the terms, right? You can say x1 square t square minus 2x1 y1 t plus y1 square. Group the terms like this and you will be able to prove all of this, right? So I have chosen my function and the function can be written like this. So what this tells us, f of t, which was written as this, x1 square plus x2 square plus x3 square minus 1 t square minus 2 times x1 y1 plus x2 y2 plus x3 y3 minus 1 times t plus y1 square plus y2 square plus y3 square minus 1. So these are two alternate versions of writing the function. Both are equivalent, but these are two different ways of writing it. We know that the first coefficient is negative. This is case 2 where x1 square plus x2 square plus x3 square was less than 1. So if it is negative, the parabola opens downward like this, right? Now there are two cases of this. Either it is a situation like this where x-axis is here and parabola has no roots, or it's a situation like this, right? We have to check which situation it is. This is discriminant less than 0 and this is discriminant greater than equal to 0, right? Okay. So let's look at the value of f of 1. F of 1 here would be basically put 1 in the first version of f of t. If you put it in the first version, you will get x1 minus y1 whole square plus x2 minus y2 whole square plus x3 minus y3 whole square minus 0, which is clearly greater than equal to 0. So that means at least at 1, the value of the parabola is above 0. So this case is cancelled. The parabola will be positive for some points at least. It has a real root basically, right? So that means the discriminant of this function must be greater than equal to 0. And now, as soon as you write the discriminant here, you will prove the inequality that you needed. Because this will become 4 times this square is greater than equal to 4 times this into this. So 4 will get cancelled and our problem is done. So the question, this one was pretty easy. You just have to set up your quadratic in such a way that you can prove that discriminant of that quadratic is greater than 0. And because of the condition given x1 square plus x2 square plus x3 square is less than equal to 1, we know that the quadratic opens in a downward facing manner. And that is always true. That is almost always obvious as soon as you try the question. So, okay, that one is done. We'll look at one last problem. The problem here says this. Let A1, A2, A100, let A1, A2 till A100 and B1, B2 till B100 be different real numbers, be different real numbers. Fill them into a 100 cross 100 table, 100 cross 100 table according to the following rule. According to the rule, what is the rule? The number AI plus BJ, number AI plus BJ is placed in row I, in row I and column J. And then second, okay, that's the rule actually. There is no other rules. And then they have said if the product of numbers in every column is always equal to 1, always equal to 1, prove that the product of numbers in every row is equal to -1. Okay. Now in this problem, first we have to get a sense of what is happening. So let's look at it. A1 to A100, B1 to B100 are different real numbers. We are filling them in a 100 cross 100 table like this. The number AI plus BJ is placed in row I and column J. And they have said product of numbers in every column is equal to 1. And we have to figure out what is the product of numbers in every row, right? So let's draw a table and try to think what is happening here. So this is row 1, row 2, and let's say this is my row I. And similarly, column 1, column 2, and somewhere here will be my column J. Column J. So the term here, row 1 and column J would be A1 plus BJ. And here it will be A2 plus BJ because it is row 2 and column J. And here it will be AI plus BJ. And here it will be row 100 plus BJ, right? Okay. So the question has said that for every J, for every column, the product of the numbers in the column is equal to 1. We are given A1 plus BJ multiplied by A2 plus BJ till A100 plus BJ is always equal to 1 for all J goes from 1 to 100. So the product of all of these numbers is always 1. And what we have to find out is product of the numbers in a row. So what is that? We have row 1 will be A1, column 1 will be B1, and it will be A1 plus B2. And it will be finally here A100 plus, no, it will be final term here will be A1 plus B100. So we have to figure out the product AI, A1 plus BI, where I goes from 1 to 100, right? We have to show that this is -1 or, and this is true for all the rows apparently, right? Okay. So we have one product where the Bj is remaining constant and A1 and all are changing. And finally, we have to get the product when A1, A2 and all are constant and the BIs are changing, Bjs are changing, right? Okay. So since it's a product of so many terms like this, we have to think maybe of polynomials and product of roots and things like that. So what I will do here is I will construct the polynomial f of x is equal to x plus a1, x plus a2, x plus a100 minus 1. Why am I making this polynomial? I know that a1, a2 and all are changing. The problem had said that the product of terms in the columns was equal to 1, right? So what was in the first? This was jth column. So we had a1 plus bj, a2 plus bj, until a100 plus bj. The product of all of this was equal to 1. So I have subtracted 1 from this function because then now I can say f of bj is equal to a1 plus bj, a2 plus bj, a100 plus bj minus 1, which is equal to 0. From here, I will be able to say that bj is a root of this polynomial, right? And actually, the question has said that this product of terms in a column is always 0 for all the columns. So therefore, j could go from 1 to 100, right? So we know that b1, b2 till b100 are roots of f of x. So that is very good information for us because now we know that it's a degree 100 polynomial and we can rewrite this polynomial like this. We can say f of x is equal to x plus a1, x plus a2 multiplied till x plus a100 minus 1. We know that it can also be rewritten as x minus b1, x minus b2 till x minus b100. Because b1, b2, b100 are roots of this polynomial, right? Now the question is pretty easy now because we have rewritten it like this. We can say substitute x is equal to minus of ai. And I can go from anywhere 1 to 100, anything. X can be any minus ai. What will happen? See, on this side, there are so many terms and there is an x plus ai term somewhere, right? So that will ensure that this product will vanish because when you put x is equal to minus ai, it will cancel one term. So it will be 0 minus 1 is equal to minus ai minus b1 minus ai minus b2. There will be one term which will be minus ai minus bi. And there will be other terms, finally minus ai minus b100, right? And now there are 100 terms here. So we can take minus 1 common power 100 and we get ai plus b1, ai plus b2, and so on ai plus b100, right? This is the product of all the terms AI plus B1, AI plus B2, AI plus B100. This is the product of the terms in the row AI, right? In the ith row, if you take the first column, the term was this. Second column term was AI plus B2. And similarly, 100th column, the term was AI plus B100, right? We are getting -1 is equal to -1 per 100, which is 1. And this is the required product of terms of any column, right? Any row, right? We have proved that product AI plus B1, I goes from 1 to 100 is equal to -1. And here I had arbitrarily chosen my I here. So I could choose I to be 2, 3, 4, whatever. So I have proved that the product of terms of any row must be -1. How did I get that? I just constructed a nice function that encapsulates the fact that the terms in the columns, the product of terms in the columns was equal to 1. So that meant that B1, B2, and B100 were all roots of this polynomial. So we rewrote it in terms of the x minus B1 factor and x minus B2 factor. And eventually it's just a matter of switching and writing x as minus AI, and we are proving the statement. Now, there is no other or nicer way to solve this problem. The problem looks like a game type of a situation. However, it's actually a polynomial problem. So that should help you understand the generality of this proof method. We are constructing different types of situations. Many times we have constructed quadratic functions or even functions of higher number of variables in order to deduce something about a problem. And in one of the problems, we even constructed a triangle, an equilateral triangle, to convert an algebra problem into a geometry problem. So this method is very general, and the limit on this is only your own creativity. So you can try and apply this in different problems, and hopefully you learned something from this video. In the next video, we will be starting a new section for the course. We'll be starting the combinatorics portions. So we'll be working with permutations and combinations and binomial coefficients, and basics of combinatorics will be starting from the next video. So I'll see you next time.